Hello and welcome back to Calculus1. We're starting chapter 4, right? And the whole chapter 4 is on application of derivatives. And the last section 4.9 is titled Antiderivatives, which is when we introduce integrals, which is backwards differentiation. We'll talk about that next week, I guess. So minima and maxima, that's first order of business. We know that mathematical functions model the world around us. We can use mathematical functions to show how infectious disease spreads. We can show how population grows. We can show how to charge or discharge battery. We build things with mathematical functions. And then we also use them in economics and business, and we have mathematical functions to model cost and profit. And we would like to know where is the minimum profit and, maximum profit, minimum cost. That's the way we want to run the business. We also want to know the maximum force maximum force or tension in a cable before it breaks due to strain, or how much weight you can put on a bridge. Can we have 17 military tanks go over the bridge at the same time, or are we allowed to have 2 maximum? You've seen the bridges that say 5 tons, right? No trucks over 5 tons. Why? Because if you put one, the bridge is going to collapse, right? So we are constantly interested in mathematics about min and a max of a function. And as I stated this at the beginning of the course, has nothing to do with the limit, because that's one of the rare cases where the wording is different in mathematics than in the language we use every day. So when you say, grows exponentially, it means both things in mathematics and in everyday talk. Grows exponentially means something is rising quickly. But when you say I'm pushing myself to the limit, you kind of want to say, you're doing your best. It's the maximum performance. But limit has nothing to do with max. We all know that the that the limit is just a way to find the y value anywhere on the function, not just min and max. So how do we find min and max? If we go back to a graph of a function that clearly has, let's say, a max in this case, and if you are to draw a tangent line on that max, what would be the slope of this tangent line? 0. Slope would be 0 because the tangent line is horizontal, and horizontal lines have 0 slope. So now we work this thing backwards. We say the slope of the tangent line is 0, but we know that the slope of the tangent line is the derivative computed at some point A, which means the derivative at that point A is supposed to be 0. So now if I give you a function, all you do is you find the derivative and then set that derivative equal to 0 to find the values where the function will have these things. Now the same thing happens if you have a minimum on the function. So if you have a function that does say something like this, there's going to be a tangent line, and a tangent line, again, m tangent is equal to 0, which means the same formula applies for both cases. So what we discovered here is that setting that the first derivative equal to 0, we are able to find these interesting points, we'll give them a name soon, at which min and max occur, obviously one at a time. So now, let's build up this theory from the beginning. First, we talk about types of min and max, and then we'll go back and redefine everything So in this situation, this point here is called the absolute max, and this one over here is called relative. The other words that are also used are global for absolute and local max. That's also used. Is this book using local or? Yeah, this book is actually using local, not relative. All right, fine, local. So observe that, yes.
So if there was another pump that was smaller, would it also be a local?
Yes. So I was about to draw one more picture. So now if you have situation like this one over here is local max. And the reason is all of these points here are higher. So in order for something to be absolute min or absolute max, it has to be the highest point, the highest y value of all y values, or the lowest y value of all y values out there. So here is the similar idea for absolute min, local min, and over here we also have a local min. So now we understand the absolute max or absolute min has to be absolutely highest or lowest point on the function. And you can see in this case, you cannot have, right, this case here cannot have absolute max, absolute min, because these arrows will go to infinity in positive or negative direction, y direction. So let's talk about when trying to find okay, so definition. We start with definition for critical point. Which is x comma y. So, an interior point of C sorry, the interior point C, there we go, of the domain of F at which F prime of C equals 0, or F prime of C does not exist, is called a critical point of F. So I will give you immediately a few examples. So say f of x is equal to x squared. You are going to differentiate this and get 2x, set it equal to 0. You get x equals 0. And if you plug 0 in original problem, you get 0. So 0, 0. There it is. Critical point. Obviously, this is a very simple example. We'll take a look at some spicier cases. Or you have f of x equals absolute x. If you draw the graph, you quickly see that at 0, 0, there is no derivative. F prime does not exist. So 0, 0 critical point. You know from your analysis of derivative from section 3.2 that to the left of 0 your derivative is -1 because that's the slope of the linear line, and on the right is +1. So what happens is that 0 derivative is trying to be +1 and -1 at the same time, which is impossible, which is the reason why derivative does not exist at that single point. So derivative for absolute x exists everywhere except at 0, 0. And by our definition of the critical point, which is the second part, if the derivative does not exist at a point somewhere, that's a critical point. Now, whether we have min or max, that's later analysis, but it is a critical point of the graph, of the function. So let's take a look at some more interesting examples from homework. Locating critical points. So I would like to see something spicier here. So problem 33 is a spicier example. It says, so 33 says find the critical points, right, for function f of x is equal to 1 over x plus ln x. So this is our f of x equals to 1 over x plus ln x. So where are the critical points? Well, let's go. Find the derivative and set it equal to 0. But before we do that, I have to bother you with domain of the function, because it is important for us to understand the asymptotes, right? Your favorite. Because those are breaks in the domain, vertical asymptotes. And then the domain, because you are not going to look for critical points on the parts of the domain where actually you have no function, right? So 1 over x graphs this way, which means everything except 0 is the domain. And then ln x graphs this way, which is only positive numbers, 0 excluded. Both of these have a vertical asymptote at x equals 0. Now, the domain here is -infinity to 0 union 0 to infinity, and the domain on the other one is 0 to infinity. So what is the overall domain? The intersection of both, right? Which is 0 to infinity. So we are looking for the critical point on this. If your calculation gives you now negative number or something, that means something is wrong. So these are some of the analysis parts that you should keep track of as you're doing these problems. So making sure that you are not looking for information on the parts of the x-axis where there is no domain for the function. So outside, you should not be looking for outside of the domain. So what's the derivative of x? Derivative of x is, we have negative 1 over x squared when we take the derivative of 1 over x. And then derivative of ln x is? Very good. Now what do we do? Except yawning. What else we do? We set it equal to 0. And then we solve the equation. So we have to solve, now we see we can move negative 1 over x squared to the other side. We get 1 over x equals to 1 over x squared. Cross multiply x squared equals to x. Now we move x to the other side, factor x, set each one of those to 0. Oh, you don't remember your algebra? Too bad. And we have two critical points. But we see that the critical point, one of the critical points landed on the vertical asymptote. We know there is a vertical asymptote at 0. So we have to throw that one into garbage. Right? We have to throw this one away because that's where the vertical asymptote is. And we are only keeping x equals to 1. Now to find the y value for it, plug in original function. And we are going to have that f of 1 is equal to 1 over 1 plus ln of 1. Well, ln of 1 is 0. So we are getting 1. And the critical point is just 1, 1. We don't know whether it's a min or a max now, but we know it exists. Now, how would you know if this is a min or a max? This 1, 1. You don't have access to graphing, right? On a test, no graphing calculators. So how do you know whether this is a min or a max? Do what? Do what? What do you mean behavior?
X over is greater than
Uh-huh. So you want to compute a point that it's, air quotation, close. That's good. So all you need to do is to compute the function at 0.9 and 1.1. We don't have yet. We will have it next class when we learn more calculus. We will have tools where we don't have to do those annoying calculations. For right now, we have to compute 0.9 and 1.1, let's say. If those values are both, the y values, are both bigger than 1, then that's a minimum. If they're smaller than 1, it's a maximum. So these are the situations that you can encounter at 1, 1. You can have a frown, you can have a smiley, and you can have whatever this is. What would that be? Like mildly unhappy. I don't know. So you see, so this is x equals 1. And if these two values, if this value x equals 0.9 and x equals 1.1, right? If their y values are less than the y value for at 1, then you have a max. If they are more, you have a min. If 1 is less and 1 is more, then you don't have min or a max. So now let's just quickly see what this stuff is. So how much is f computed at 0.9? You can use your abacus to do that. So you have 1 divided by 0.9 plus the ln of 0.9. So let's see. 1 divided by 0.9 plus ln of 0.9. And I have value that it's larger than 1. And then I repeat the calculation for 1.1, right? Because it could be this case, when one side is smaller, one side is bigger, and we call that inflection point later on. We didn't learn about those yet, but it could happen. So 1 divided by 1.1 plus ln, ln of 1.1. Also larger than 1, so 1 is minimum. Because when you move a little bit to the left and a little bit to the right, both of these points are higher than our 1. So 1 must be minimum and then go up into the other two values. So don't go far. Don't go 1 unit because you don't want to jump the asymptote. As you can see, in quotation marks, let's say I still stay close to number 1 as I'm computing. One more example. Trying to find stuff that you would definitely like. Like problem 35 says f of x is equal to x squared times the square root of x plus 1, I believe. Yep. So what's the domain for this function? We know that we can feed anything into x squared. Positive, negative, 0, doesn't matter. But under the root, we can't. So I hope you guys see that you cannot feed values smaller than x negative 1. Because when you are dealing with the domain for these guys, you know that argument needs to be larger or equal than 0. If you solve this, anything larger than equal to negative 1 is the domain. So that's our domain. That's the more restrictive piece. That's square root. So now, go ahead. Take the derivative, f prime of x, set it equal to 0, solve the equations. All right, I'll give you 18 seconds. No question. No problem.
times the limit price.
So this is what? Anyone? This is derivative. Which rule do we have to use? Product rule. So copy the first times derivative of the second plus copy the second times derivative of the first. So I'm going to simplify this and then set it equal to 0. This is x squared over 2 square root of x plus 1. Oh, actually nothing to simplify here. It's just this. All right. So when you have something like this, two terms equal to 0, you move one term to the right, and then you can cross multiply. It's a fairly simple thing. If it's going to make you happy, you can put over 1, and then cross multiply. So we get x squared is equal to negative 4x times x plus 1, because square root times square root cancels. So x squared is equal to negative 4x squared minus 4x. And then 5x squared plus 4x equals to 0. We factor out x, 5x plus 4, from where x is equal to 0 and x is equal to negative 4/5.
Professor, couldn't you also just rationalize it instead of doing the cross multiplication after you get x squared over 2 root x plus 2x?
Where? Here?
X, yeah, right there, and that's that you can multiply the.
But if you you are not solving the equation in that case.
Yeah, I know, but then you would get, once you do the algebra, you get 5x squared plus 4x, and then you set that equal to 0.
Well, yeah, whatever, sure. Good. Domain is any value larger than negative 1. Both of these values are larger than negative 1, so we get to keep both. And we can actually compute. So when x is equal to 0, f of 0 is 0 squared times square root of 0 plus 1, which is 0. So first critical point is 0, 0. And when x is equal to negative 4/5, that's f of negative 4/5, negative 4/5 squared times negative 4/5 plus 1. So now we compute this. What do I get? I get 16 over 25 times the square root of, and now you have 1/5 over here. So this is 16 divided by 25 root 5, and then we hit root 5 on top and bottom to simplify. We get 16 root 5 over 125 as the x value, so negative 4/5 and 16 root 5 over 125 is the second. So those are the two critical points that we were looking for. All right, so there's one more piece to this. We'll finish it next time, and make sure you work on the project tomorrow. So I'm going to upload that now and open up the project as soon as you can. 3 problems, read that stuff, and start doing.